Welcome students. Here we are explaining the Bernoulli's equation. So let's start with the equations of motion. According to Newton's second law of motion, net force acting on a fluid element is equal to mass of the element multiplied by the acceleration. So this is the equation for equation of motion according to Newton's second law, that is Fx is equal to m into Ax. So in fluid flow, the forces present are the gravity force, the pressure force, the force due to viscosity, turbulence and compressibility. So the force acting on a fluid element is the resultant of these five forces. So and the resultant of those forces is equal to mass multiplied by acceleration. So the resultant of all these forces is Fx, and if we sum the forces we will get Fx. So if we consider that the force due to compressibility is negligible, then the resultant force is a sum of four forces. That is gravity, pressure, viscous force and force due to turbulence. So this equation is called Reynolds equations of motion. Again, if we consider turbulent force is negligible, we get the equations that is called Navier-Stokes equation. So here the resultant force will be the sum of gravitational force, pressure force and viscous force. The turbulent force and the compressibility force is negligible. Again, if we consider that the viscous force is also zero because the fluid is assumed to be ideal, then the equation of motion is called Euler's equation of motion. Okay. So the Euler's equation of motion says that the net force acting on a fluid element is the sum of forces due to gravity and pressure. Okay, so let us consider a fluid element which is moving along a streamline. Streamline is a layer of a fluid in motion. Okay, so this is the streamline. The streamline is in a direction S. So direction S is specified here. Okay. Then let us consider a cylindrical element along the flow. This is the cylindrical element. It has a cross-sectional area of dA and a length of ds, which is also marked in the figure. ds is here. dA is the cross-sectional area of this element. Right, this is dA. Okay. So the forces acting on the cylindrical element are first pressure force in the direction of flow, that is here, this direction. Okay. Next is pressure force opposite to the direction of flow, that is this direction here. Next, the weight of the element. Weight of the element acts directly downwards. Okay. So pressure force is pressure into area, that is P into cross-sectional area dA. And pressure force opposite to the direction of flow is P plus dou P by dou S into ds into dA. Here pressure along the direction of flow plus pressure inside the fluid element is also considered. So this term comes into play, dou P by dou S into ds. And there is the weight of the element, which is given by rho g dA ds. That is volume into density gives you mass, mass into g gives you weight. Okay, this quantity is the volume dA ds. That is area of cross section into ds, that is length. The volume of a cylinder is given by pi r square h, that is cross sectional area into multiplied by height of the cylinder. So dA ds into rho gives you volume, density into gives you weight, mass, density into volume gives you mass into specific acceleration due to gravity gives you weight. Here in this figure you can see that the pressure force opposite to the direction of flow is taken as P plus dou P by dou S into ds into dA. Here there is one term, we have taken dou P by dou S into ds. This is actually dou P by dou S, where it is the pressure intensity per unit length of the element. The length of the element is ds. So dou P by dou S is the pressure intensity per unit length. That is, dou P is the pressure inside the element divided by dou S, dou P by dou S multiplied by the length of the element ds. So this is the pressure exerted by the fluid inside the element. So pressure intensity per unit length is multiplied by the total length, and the direction of that force is in the opposite direction. So let theta be the angle between the direction of flow and the line of action of the weight of element. So this is the line of action of the weight, and this is the direction of flow, which is the direction of the streamline. So angle between these two directions is theta. Okay. So the resultant force is the resultant of the three forces, that is the two pressure forces, and the third force is the weight. Okay. So first force is here, PdA. The second pressure force is in opposite direction. So we have a negative sign here, that is here. Again, the weight is also acting downwards, and the weight has two components, right? Weight is acting downwards. So it has two components, one along the streamline and one perpendicular to the streamline. So this component is the adjacent component, so we consider it as the cosine component. So that is rho g dA ds cos theta. So this whole equation is there, and this is the resultant force, and the resultant force is actually the product of mass and acceleration. So mass is here, rho into this quantity is the volume V, right? dA into ds is V. So rho into V gives you mass, multiplied by AS gives you Fx. Okay. And we also know that acceleration is dV by dt, that is change in velocity with respect to time. And this can be written as dou V by dou S into ds by dt plus dou V by dou t, which is equal to, again, ds by dt can be written as V. Velocity is the change in distance with respect to time. S is distance or length. So here ds by dt, this term becomes V. So we have V dou V by dou S plus dou V by dou t. Okay. So we got this. Again, if flow is steady, dou V by dou t is equal to 0. Then we have AS is equal to V dou V by dou S. That is, this term dou V by dou t has become 0. So AS is equal to V dou V by dou S. So substituting this equation of AS in equation 6.2, that is, this is equation 6.2. Okay. Here we have the term AS on the right hand side. Okay. Right. Okay, so minus dou P by dou S into ds dA minus rho g dA ds cos theta, which is equal to rho dA ds into dou V by dou S. Here the equation 6.2 is simplified, that is, the bracket was there on the second term. So that bracket is opened and denominator is multiplied. So we have here dou P by dou S into ds dA minus rho g dA ds cos theta is equal to rho dA ds into dou V by dou S. Okay, and divide by this term rho ds dA, then we get the equation as, finally, rearranging the terms, dou P by rho ds, rho dou S plus g cos theta plus V dou V by dou S is equal to 0. If we see the figure, we find that cos theta is equal to dz by ds. That is, if we check this figure, this angle theta is this angle, and this is the length of the cylinder, which is ds. This is the vertical direction in which the weight is acting, and vertical direction is taken as z here, so dz. So from here, if we take cos theta, we find adjacent side by hypotenuse, that is dz by ds. This we can be substituted into this equation. So that becomes 1 by rho into dou p by dou s into g into, instead of cos theta we substitute dz by ds plus v into dv by ds is equal to 0. And we take ds as common, so ds is cancelled from all terms, so that becomes dp by rho plus g dz plus v dv is equal to 0. So this equation is called as the Euler's equation of motion. And Bernoulli's equation is obtained from the Euler's equation of motion, that is, we considered a fluid element. So if we integrate the equation, okay, so rho is a constant if we assume that the flow is incompressible. We have already assumed that the flow is non-viscous, that is, it is an ideal fluid and there is no turbulent force. So if we also assume that the flow is incompressible, then rho is a constant. So rho need not be integrated. So dp is only integrated, which becomes p by rho. Again we have g into z, that is when dz is integrated, and integral of v dv is v square by 2. So the equation finally rearranged comes to p by rho g plus v square by 2g plus z is equal to constant. This is the Bernoulli's equation, in which p by rho g is the pressure energy or the pressure head, v square by 2g is the kinetic head, and z is the potential head. Some assumptions made while deriving the Bernoulli's equation are, that is, the fluid is ideal, that is viscosity is 0. The fluid is steady, that is dv by dt is equal to 0. There is no variation of velocity with respect to time. And the flow is incompressible and the flow is rotational, that is, there is no turbulence. And in case of real fluids, they are not non-viscous, that is, viscosity is never 0 for a real fluid. Real fluids are viscous and they offer resistance to flow. Hence, there is some loss in the fluid flow. Some energy is lost for the motion or the flow of fluid. So that losses have to be taken into consideration. Okay. So if we consider a fluid flowing at for a distance, and we assume that the fluid is flowing from point 1 to point 2. Okay, so at point 1 the state of the fluid is in such a way that P1 by rho g plus V1 square by 2g plus Z1. This is the pressure head, kinetic head and potential head at section 1. And this is the Bernoulli's equation for the real fluid at section 2, that is pressure head plus kinetic head plus potential head. And these two are equal only if we account for a loss in head, that is HL, between these two sections. That is, when the fluid started its motion from section 1 and reached section 2, it lost some energy or head, that is HL, which is the loss of energy. That must be added to the Bernoulli's equation for real fluids. This is a pictorial representation of Bernoulli's equation. So here you can see this is section 1 and this is section 2 of a pipeline. So this is the pipe. Okay. So Bernoulli's equation is applied to a pipe section and you have two sections 1 and 2. So the direction in which fluid is flowing is here. So this section has an area of cross section A1 and this section has an area of cross section A2. Okay. So at this section, if you consider the pressure head is P1 by rho g, that is the pressure inside the fluid is P1 by rho g, or the pressure head is P1 by rho g. The kinetic head is V1 square by 2g and the potential head is Z1. Potential head depends on the height of the liquid surface or liquid column. And if we consider section 2, the pressure energy is P2 by rho g, or pressure head is P2 by rho g. Kinetic head or kinetic energy is V square by 2g, V2 square by 2g. and potential head is Z2. Okay, so if we consider section 1 and section 2, the total energy is this much at section 1, the total energy is this much at section 1, right, but here it becomes only this much. That is all the three energies summed up together. So we can see that compared to section 1, at section 2 there is an energy loss. So that is HL. So practical applications of Bernoulli's equation are venturi meter, orifice meter and pitot tube. Thank you.